G'day folks. In my last video, we had a look at quadratic equations and how to solve them. In particular, we saw this wonderful formula called the quadratic formula, which allows you to compute exactly the roots of a quadratic equation. So I thought it would be interesting in this video maybe to have a more historical look about this notion of solving a polynomial equation. So basically, there's two questions we want to look at. The first question is, when can an equation be solved? Let me give you an example. Because we've been looking at quadratics, consider the following quadratic equation. 3x squared minus 15x plus 16 equals 0. Now, I could plug this into Google perhaps and ask Google to find me where the roots are, or you could use Mathematica or Maple or whatever computer package you want. And there's certainly algorithms that can find you numerically the solutions to these types of equations. So if you use one of these packages, you plug it in, the package will tell you there are two roots to this equation, 3.45 something or other, and 1.524 something or other. Both of these expressions, they are numerical approximations to the true solution to this equation. So here you would say, yes, I found the roots, but only to a certain accuracy, because I can only write down a finite amount of the decimal expansion of these numbers. On the other hand, the second question I want to look at is, when can we find exact solutions to a particular polynomial equation? By exact solutions, I mean an expression involving integers and maybe square roots and cubed roots and fourth roots, linear combinations of these types of terms, but an expression for the roots of the polynomial in terms of the coefficients of the polynomial. We've already seen this for quadratic equations, because for quadratic equations, we have this wonderful tool, the quadratic formula, that finds you the roots of this polynomial here in terms of the three coefficients, A, B, and C. So if we use the quadratic formula on our example over here, 3x squared minus 15x plus 16, the quadratic formula will tell us the following. The exact solution to this equation, there's two of them, 15 plus the square root of 33 over 6, and 15 minus the square root of 33 over 6. To my eyes, exact solutions look beautiful. They tell you the full story. Numerical solutions, whilst very useful, they can only give you the answer up to a certain accuracy. Think of it this way. If I told you that the solution to a particular equation was 1.000000000 to 10 decimal places, you'd naturally think that the answer is 1. But you don't know that. You only know a finite amount of the decimal expansion. So there's a limitation to using real numbers. Okay then, let's delve back into a bit of history. Oops, I think I've gone too far. So maybe to prehistoric times. So imagine there's a woolly mammoth out there on the icy tundra, and you've got a couple of cavemen, Og and Bog. They're chewing the fat. And maybe this is about 10,000 BC. I'm pretty shady on history. And one of these cavemen, Og, he's out there and he's counting woolly mammoths. So what does Og do? He goes, 1 woolly mammoth, 2 woolly mammoths, 3 woolly mammoths, etc., etc., etc. Guess what? Og's invented the integers. So the integers have been around forever and a day, really. Maybe we could go a little bit further in time. Prehistory is an awful long time ago. The first major civilization, maybe in a sort of more modern sense, was, or rather occurred in the Mesopotamia region, the time of the Sumerians. So the Sumerians were, I don't know, approximately 5000 BC for a couple of millennia or so. They were replaced by the Akkadians and the Babylonians. So the precise region where Mesopotamia is located is sort of southern Iraq and a bit of Iran and Syria today. So they were great architects, these guys. They built huge grain storage facilities called ziggurats. They did a lot of agriculture. They were intensive farmers. And they also had the earliest form of writing. So this is a clay tablet from this region, which was sort of dated back to about 2000 BC, I think. The Hanging Gardens of Babylon were one of the ancient wonders of the, well, one of the wonders of the ancient world, I should say. They were also interested in baking. They absolutely loved cakes, the Sumerians and the Babylonians. And the thing about it, eating cakes is if you turn up at a party and you eat the whole cake, that's really bad for your health. You need to cut the cake into pieces. So you could think of the operation of cutting a cake into pieces as developing the idea of a fraction. For example, you don't want to eat the whole cake, you might want to eat 1/10 of the cake. So the Sumerians and the Babylonians gave us fractions. In fact, they worked to base 60. So they could do quite complicated mathematical calculations at base 60. It's thanks to the Babylonians that we have 60 seconds in a minute and 60 minutes in an hour, 360 degrees in a circle. Jumping forward in history, well, thousands of years actually, we had the time of the Roman Empire. Romans themselves were more interested in conquering people perhaps than in the academic side of things. It was more the Greeks at the time who were the philosophers and the poets and so on. This is a picture of Pythagoras of Samos. He would have been around maybe, I think, around 570 BC to 500 BC, or approximately that time. He founded a sect or a school in a place called Croton, which is in southern Italy. And they were basically a collection of philosophers and mathematicians. The theory of trigonometry was one of the obsessions of Pythagoras. And once you start talking about right-angled triangles, that immediately leads you on to Pythagoras' theorem, x squared plus y squared equals z squared, and then you're looking at quadratic equations. So Pythagoras was very interested in exact solutions to quadratic equations. He believed the whole world was governed by square roots of numbers, which we now know isn't true. He was also a controversial figure at the time, and the Pythagoreans, the sect that he founded, eventually they were overthrown by a bunch of angry villagers with pitchforks. Some people believe that Pythagoras was killed in the uprising. I suppose we'll never know today. Okay, then jumping forward in time, people were mostly not thinking that much about mathematics in Europe anymore. So the emphasis shifted to China and to Persia. The Persians and the Chinese, there's records of them studying cubic equations, which are degree 3 polynomials. Remember, a quadratic equation is degree 2. A cubic equation is degree 3. And you can ask the same kind of questions. So remember, if we go back to our quadratic equation, which we can now solve exactly thanks to the quadratic formula, we could say the quadratic formula provides a complete solution to where the roots of a quadratic equation lie. So once you've dealt with quadratics, the next stage up is to look at degree 3 equations, cubics. So in the 7th century, there was a famous Chinese mathematician called Wang Xiaotong that was part of the Tang dynasty. He studied these equations, and then a couple of Persian mathematicians entered the scene. In the 11th century, you had Omar Khayyam. He was both a mathematician and a poet. He was the author of the Rubaiyat of Omar Khayyam, but he also solved various types or subclasses of cubic equation. He'd find exact formula for a certain class of cubic equations. And then in the 12th century, building on from that, was the mathematician, also from the same region, Sharaf al-Din al-Tusi. He studied further cubic equations, and also there's the work of the Indian mathematician Bhaskara at the time. Well, what was happening in Europe at this time? Unfortunately, sort of the first half of the second millennium, Europe fell on dark times. I guess that's why we call it the Dark Ages today. There wasn't much mathematical work going on because people were just intent on surviving. There were all kinds of wars going on, religious persecution, plagues, you name it. It wasn't a happy time to be alive in Europe, I guess. So really, the Dark Ages, they lasted until the time of the Renaissance, which was sort of 15th century. And the church at the time was very anti any kind of scientific learning, which of course was a huge impediment to developing further work on these polynomial equations. Intriguingly, the next major progress was made in Italy, and this was sort of 15th, 16th centuries, I guess. Believe it or not, negative numbers, or rather the notation for a negative number, the minus sign, this only really got adopted in Europe in the 15th century. And that's because the European mathematicians at the time were translating a lot of the Persian mathematical works into Italian and Latin, I guess. And it's then that the minus sign entered common usage, which is quite surprising if you think about it. So obviously the Renaissance was a wonderful time to get stuck into studying mathematical equations again. And foremost was the use of this negative sign. So now Og has a notion not just of positive numbers of woolly mammoths, but negative numbers of woolly mammoths. Lucky Og. A major figure at this time was an Italian Renaissance mathematician called Girolamo Cardano. Remember my last video at the very end, we accidentally encountered this number, the square root of -1. He was the evil genius behind the adoption of the square root of -1 in mathematical parlance. He had a student, Scipio del Ferro. I looked everywhere. Sorry, this is a really bad joke. I looked everywhere for a picture of Scipio del Ferro. No such pictures seem to exist, certainly on the internet. So his Australian counterpart is Skippy del Ferro, the bush kangaroo. Sorry. Well, going back to Cardano, he invented the square root of -1. Like I mentioned, it takes a lot of imagination if you're Og the caveman to imagine what the square root of -1 woolly mammoth looks like. But there you go. But once you have the square root of -1 in your arsenal, things become much easier for you. So Scipio del Ferro, he actually found the cubic analog of the quadratic formula. Remember, the quadratic formula tells you where the solutions to your quadratic equation, how to express them exactly. The cubic formula does the same trick. So once you know about the square root of -1, finally, the general solution to this type of equation, you can write it all down. If we go back to our little checklist, we can now cross off not just the quadratic formula, but the cubic formula as well. I mean, I should maybe point out at the time there was a lot of controversy about who actually did come up with the cubic formula. If you like Real Housewives of New York or whatever, this is right up your alley. There's nothing like a good feud. So at the time, another fellow, Niccolo Tartaglia, he alleged that Cardano and his student had stolen his formula. And there's actually quite a bit of historical evidence in support of Tartaglia. So the story goes, Cardano was discussing with Tartaglia at the time these types of equations, and Tartaglia said, oh, I've got a general solution to the cubic. And rather than tell him directly, allegedly he put it in a poem, which he sent to Cardano, and he said, don't publish this poem, whatever you do, but this gives you all of the details, if you like. So about 10 years later, I think Cardano just said, oh, bugger it, I'm going to publish the poem. And then there was this massive feud between Tartaglia and Cardano. Tartaglia felt betrayed, all kinds of hijinks took place. It's quite sad. Tartaglia himself, he died in destitution, his reputation ruined. It just goes to show how excited mathematicians can get about particular formulas. Well, you could ask yourself, we've got a quadratic formula. Thanks to the 16th century mathematicians, we have a cubic formula. What about a quartic formula? How long do you think after the development of the cubic formula did it take mathematicians to find a quartic formula? Was it 100 years or 200 years? You'd be surprised by the answer. It was only a couple of years later that the quartic formula was found. I'm not going to write it down for you because it's quite involved, but the person who developed it was one of the associates of Cardano. His name was Ludovico Ferrari. So you can write down an exact formula for the roots of a degree 4 polynomial, just as you can for a quadratic and a cubic, which is wonderful news. That makes you think, well, hang on, maybe a quintic formula is on the cards as well, because if you can do degree 3 and degree 4, the next obvious step up is degree 5. Well, some progress was made. Here's a picture of the mathematician Leonhard Euler. He worked on certain classes of quintic equation, and also Lagrange as well did. But the general formula seemed elusive. So even though it only took a couple of years to go from the cubic to the quartic to the quintic seemed a lot more difficult. I mean, when you look at the exact expression for the quartic, it's nasty. So you can imagine that the quintic would be super nasty. Well, this leads me on nicely to the main topic of today's video, which is the life of Évariste Galois. So historically, when did we have the French Revolution? That was about 1789. So up until 1789, the French had had a monarchy for a long, long time. And then they finally got fed up of being poor and oppressed, and they threw out their monarchy during the French Revolution. there's nothing as wonderful as a revolting French person. Not that French people are revolting, they're actually lovely people, but they love having revolutions. So they kicked out the monarchy at the time. They beheaded a lot of them. And then you had, I suppose, Napoleon. He came and basically involved France in lots and lots of wars overseas till the French eventually got fed up with him. And then what might not be well known is for a short period after Napoleon, the French reinstated a monarchy. It wasn't as strong a monarchy as the previous regime, but it was at least a nominal monarchy. So it was around this time, maybe about 1811, I think, that Galois was born. So he was born in a place called Bourg-la-Reine, which is in the south of Paris. His father was the town mayor. His name was Nicolas Gabriel. The only known picture I could find of Galois is this picture here. It's not particularly satisfactory, but for some reason, there's not that many portraits of him that are available. So he entered school at the Lycée Louis Lagrange when he was about 12 years old, and he got very interested in mathematics. In particular, he started reading the book of Legendre called Éléments de Géométrie, and also he became interested in Lagrange's work at the time. So you may not be familiar with how the French system works, but they have these special universities which are almost above the level of the universities. They're called Grande École, and the best school for mathematics at the time was the École Polytechnique in Paris. So Galois tried to get into École Polytechnique, but he failed. He was not a diplomatic soul. He would argue with his teachers that he was correct and that they were wrong, and nobody likes to hear that they were wrong. So eventually they just thought, this guy is such a troublemaker. There's no ways we want him at École Polytechnique. So instead he went to l'École Normale, which was a sort of not as good a level school as École Polytechnique at the time. This was also a time of a lot of political turmoil. So remember, you had the first French Revolution. The major French Revolution was in 1789. And then after Napoleon and the restoration of the monarchy for a time, there was actually a second uprising or revolution, not as famous as the first, but still a major historical event. And Galois was a very political figure. He was a Republican, as was his father, and he became very involved in this second French Revolution. So remember, Galois was multitasking at the time. He was doing his mathematics, which was all about questions related to a quintic formula and when you can solve a particular polynomial equation. But simultaneously, he was also being a political activist. If you want to read more about this, there is, of course, Victor Hugo's famous book, Les Miserables. It's a fictional story, but it is set within the time of this second French Revolution when you had the student uprising in Paris. I just mentioned that. Galois was a contemporary of many famous figures. Here's Victor Hugo. He wrote Les Miserables, and he also knew or was associated with Alexandre Dumas, who wrote the Three Musketeers. So what did Galois do? He was working away on his theories, and at the time, every year there would be a mathematics competition in France called Le Grand Prix. Don't confuse that with Formula One, that's something different. Every year, mathematicians would submit their work to Le Grand Prix, and the winner would obviously get a lot of kudos from and enhancement to their reputation by winning this competition. So Galois submitted his work on solutions to polynomial equations to a famous mathematician called Joseph Fourier. So this was about 1830. Unfortunately, Fourier was very ill at the time, and he died soon after receiving Galois' manuscript. So unfortunately, Galois' work kind of got lost to the general populace. And I suppose Galois became more politically influenced and maybe put his mathematics a little bit on the back burner. In fact, the story goes, he was at a dinner party and he proposed a toast to the then monarch of France, who was Louis Philippe. So Louis Philippe was very, very unpopular amongst Republican figures. And Galois allegedly said, he made a toast, and he said, "To Louis Philippe's health until he betrays," and he raised a dagger above his cup. And in the audience were some monarchist infiltrators, I guess, spies. They heard this comment, reported back to Louis Philippe, and so what happened was they arrested Galois and they held him in Saint-Pélagie prison in Paris. He was also thrown out of l'École Normale at the time, so he's very much on a downward spiral, poor chap. Yeah, so he's thrown out, he was imprisoned, and his prospects were pretty bleak because his reputation was now in tatters. Okay, then, after being thrown out of l'École Normale, he left the prison and returned to make his ends meet by taking up the role of a maths tutor, whilst at the same time he was finessing his theories. But Galois, you can't keep a good man down. He was back at the politics very soon afterwards. He went on a march. He was at the head of the march against the monarchy, and he was arrested once more. So I think he must have spent probably a total of about 6 months in prison during this period of his life. Fortunately or unfortunately, there was a cholera epidemic in Paris at the time, so they threw out the sort of fairly minor prisoners from all of these prisons, which meant that Galois again got released. And now the story gets really interesting. So at the time, allegedly, according to certain people's accounts, Galois fell in love with a mysterious lady whose name we don't fully know. This is all a matter of conjecture. There's various competing theories. It's really interesting just to get stuck in and listen to people's YouTube accounts of Galois' life. I mean, my account that I'm giving you today is about 5 or 10 minutes, and it's really, pretty appalling, if I'm being honest. Go and watch the proper videos about this thing. Anyway, Galois falls in love, or so the legend goes, but he's challenged to a duel by somebody who's either in league with Louis Philippe or at least doesn't like Galois at all. So Galois allegedly, I mean, this is a total myth in my opinion, the night before the duel was due to take place, the legend goes that he wrote down all of his theories on how to solve these polynomial equations, and I don't believe that for a moment. If he had any sense, he was practicing learning to shoot. So anyway, there was this duel. The duel took place on May the 30th in 1832, and Galois, unfortunately, he wasn't a great shot. He got hit in the abdomen, in the guts, and a day later, unfortunately, he died, just at the age of 20. So rather than writing down his theories, he should have been learning to shoot straight. They buried his body in a common grave in Montparnasse Cemetery. You can wonder, If Galois had lived beyond the age of 20, suppose he'd lived to the age of 60, what other wonderful mathematical theories would he have come up with? Anyway, why am I telling you about this guy, Évariste Galois? It's because Galois showed something amazing. He showed that it's not only difficult to find a quintic formula, it's impossible to find a quintic formula. There are some equations, some polynomial equations, that no matter how hard you try, you will never be able to find an exact solution to them. So going back to our checklist, here's a little bit of negative news from our friend Évariste Galois. Unfortunately, it can't be done. There is no general quintic formula. Similarly, there's no sectic formula. You can't solve a general degree 6 equation. What would 7 be? Is it septic? No, that doesn't sound. Anyway, there's no degree 7 equation either. So this is as good as it gets. It stops at degree 4, and beyond this point, we're all at C. We will never be able to find exact solutions to our equations. What does that mean in concrete terms? It means you actually do need a calculator. I've spent the first couple of videos dissing calculators, but honestly, you do need calculators. So maybe the last video I give you should be on how to use your calculator properly. Anyway, before I end up, I do want to encourage you to get stuck into learning about the history of mathematics. It's really interesting. The feud between Cardano and Tartaglia, that would make a great movie in my opinion. Likewise, the life of Évariste Galois would be another fantastic film, especially if you like Real Housewives of New York.